The next speaker is Xuanli, and she is talking about RO impacts and advances in NOAA NWP operations.
Thank you, Harold. So I'm going to talk about the RO impact and advances in the NOAA NWP operation. First off, I'd like to acknowledge my colleagues at NCEP EMC, and also my collaborators, Chris Riddle, Lydia Kukura at COSEP, and also Jeremiah Schubert and Rick Antes at UConn. So in this talk, I'm going to firstly give an overview of RO data simulation in the operational GFS and the GDAS system at EMC, and then demonstrate some of the data impact, mainly the commercial impact on the GFS forecast. And then I'm going to share some of our recent results on the collaborative work RO optimization with the COSEP and UCAR, and then wrap up with the future directions. So currently, the operational GFS and GDAS, we use FA3 dynamic core. The resolution for the operational run is 13 kilometer, 127 vertical levels, and the model top is 80 kilometer. And for physics, we use GFDL microphysics. And for the current operational GDAS, which is version 16, we use GSI-based hybrid 4D MBAR. And 13 kilometer as the deterministic forecast and 25 kilometer for the ensemble and 80 ensemble members. For some of the details, we use 4D IAU and LETKF ensemble update. And we assimilate different types of observations. If you can see this chart over here, these are the current missions that we operational assimilate into the GDAS system. The blue ones are actually assimilated, and the orange ones, the Grease follow-on and Sentinel 6, they are actually in monitor mode. And for the RO ops operator and the ops area, we use Ruger 2002 for the total reflectivity. And the operator is MBAM 1D bending angle developed by Lydia Kukura. The observation area is developed using the Rosier's method. On the red panel, the figure that this is the global average of this ops error. The ops error is a 2D function, polynomial function of latitude and the impact height. As you can see at upper level, especially above 45 kilometers, the ops error is actually pretty large. So for quality control, we have different quality control filters, including the superfraction, which checks the bending angle below 5 kilometer impact height using two different criteria. And we reject data below model level 3. And we have a gross error check, which use O-B over error. And for the METOP data, we rejected the data below 8 kilometer impact height. We realized that this is good data, and we're thinking of bring this METOP data back, but it's gonna in the future. And one of the major QC in the MBAM operational RO assimilation package is this called the statistic QC. Which was developed by Lydia in 2013, summarized in this paper. This QC use O-B over observation error, and with the different threshold values, X times of the sigma. And on the right, this is the rejection rate from different types of QC filter. The purple one you can see. This is the statistical QC. So below 10 kilometer and above 35 kilometer, it actually filters quite a bit of data, about 20%, above 20%. And below 5 kilometer, you can see this superfraction actually filters quite a bit of data. For commercial data, we reject the data above 45 kilometer. And commercial RO data, I think Natalie and other CDP talks already covered this, so I won't repeat this. But currently, there's one thing I wanted to say about this is currently we're working on testing some of the sample data for DO4, the SPIRE data. So once we get a clear idea on the impact of the data, then we can decide whether or not to move forward for that one. And for the commercial data impact, I wanted to demonstrate the assessment experiment. This one is for the RODB1 DO4. This is actually the largest data buy from March of 2022 to January of last year. And we have conducted a verification experiment, which is a data denial experiment. And the control run is using the operational system with the simulation of the DO4 data, which include 500 from GeoOptics and 5,500 from SPIRE. And the data denial experiment DO4 was conducted using, well, both of them are using half resolution, 25 kilometer resolution without the commercial data. So I have two figures over here. On the left, this is the percent of observation passing QC. As you can see, the commercial data, red is SPIRE and blue is GeoOptics. They're quite close to Cosmic 2. And on the right, this is the OMNSB over B bias and RMS. As you can see, the commercial data actually has a smaller RMS below 10 kilometer. Actually all the way back up to the 35 kilometer, if you take a closer look. So data impact, this is the plots for fit to radiosonde data. You can see there's when the DO4 commercial data was assimilated, the bias in temperature in troposphere, mid to low troposphere, is actually getting slightly larger. And for relative humidity, we got a significant impact, improvement in relative humidity. And on the right, this is the RMSE, observation minus forecast. You can see that the RMSE in wind is getting better. So this is scorecard fit to ECMWF analysis. Because this is a data denial experiment, so green means degradation and red means improvement. So it is good to see those red triangles over here. This is especially significant in Southern Hemisphere for anomaly correlation, RMSE, especially for wind and temperature. But for bias, especially the geopotential height, it is quite a challenging in both Northern Hemisphere, Southern Hemisphere, and tropics. And moving on to the verification experiment for RODB2, this is for DO2 planet IQ data. And for this experiment, we use full resolution, 13 kilometer resolution, and the control is actually the operational run, the GFS. The verification period is from July to August of last year. And the planet IQ data is about 2,600 profiles per day during that period. So on the figures over here, this is observation passing QC in the middle. Red one is Planet IQ. So you can see Planet IQ is actually pretty close to Spire. At this time, the Spire is the UMSS Spire data. And on the right, this is ominous B over B for bias and RMSE. So Planet IQ is actually got a smaller RMSE from 20 kilometer to 35 kilometer, but at below 5 kilometer, the RMSE is slightly larger. And this is the scorecard fit to ECMWF analysis. Overall, the impact is neutral to slightly positive. So you can see in these plots, green means improvement and red means degradation. So improvement was seen in Southern Hemisphere for wind and the temperature for RMSE. And we actually also see impact in Northern Hemisphere as well for wind and the temperature. For most of the recent experiments that we have done, including the collaborative ones, we use GFS V17, which is still under development. And V17 is actually quite different from V16. V17 is a coupled system. It's a 5-way weakly coupled between atmosphere, ocean, ice, waves, aerosol, and land. And in the atmosphere DA, we incorporated several major updates. One is the usage of Thomson microphysics. It's a double moment microphysics. And some of the upgrades for Oscar radiance. And we also use scale-dependent localization. And we also included during this time period, some of the new observations from satellite radiance, the GNSS-RO data in is scheduled, and also Sidewind and sail drone data. For our collaborative work with COSAP and UCAR, we're testing this, UCAR developed this new hybrid ops error model. So we're working with COSAP to do the testing and to see how that helps the RO assimilation. So for this ops error, as you can see on the conceptual plots over here, it is divided into 3 vertical regions. Below 10 kilometer, we use a fractional LSW. And from 10 kilometer to 30 kilometer, it is a constant relative error of 1.25%. And above 30 kilometer, this is the blue region. We use STD 4060 to estimate the ops error. And this is the comparison between the old ops error and the new ops error on the left. This is 3-panel plots. Left is the old ops error. In the middle, this is the new ops error. And on the right, this is the difference between these two. So you can see below 10 kilometer, the new ops error, when we use the hybrid one, the ops error get increased. And above 10 kilometer, especially above 30 kilometer, the ops error was decreased quite a bit. And we realized that not all of the missions has LSW available. So for those that are not available, we use hybrid, the 3-corner hat estimated ops error, which is plotted over here. Right. And we're also exploring the usage of a new QC. The previous statistic QC filters a large amount of data. So this new QC use a different criteria. We use O-B over B and the threshold value as 3 times of sigma. So here's the plots. On the left, this is the current QC, the statistic QC developed by Lydia. And in the middle, this is the new QC. On the right, this is the difference between these two. So you can see below 10 kilometer and above 35 kilometer, we have bring into the system a large amount of data, up to 50%. Okay, so this is the result for the new ops error, new QC. On the left, this is the forecast bias, O minus B over B. And on the right, this is RMS for O minus B over B. And the three panel plots left were dividing into topics, Northern Hemisphere and the Southern Hemisphere. Black one is control and the red is the new ops error, new QC. As you can see, when the new ops error, new QC was used, the bias gets smaller, about 45 kilometer in all three regions. And below 10 kilometer, below 10 kilometer, especially 5 kilometer, it gets larger. And RMS is apparently gets larger for RMS, about 35 kilometer and below 10 kilometer. The main reason is because we bring back a lot amount of data in those two regions. And this is a scorecard from the comparison between the control is the old QC, old ops error, and the experiment is the new QC, new ops error. So green means improvement and red means degradation. We can see the impact overall is neutral, but we do see the degradation in topics for RMSE for height and the bias in height. So this is my last slide. Future directions. We're using V17 or ROMAX experiment as an opportunity to explore the potentials for GFS V17 and also working on this optimization for the ops error and the QC. One of the major efforts here at EMC is to the transition to JEDI. And because JEDI is our next generation of DA infrastructure. And V17, we still use GSI as for the atmosphere DA, but from V18, it is all entirely JEDI-based. And the current status for the T2O transition to operation is that we have completed most of the data type from reading into buffer file to using the ops operators to calculate the H of X and then write out the diagnostic files. And the next step, we're going to test in the cycling part. There are several of the things that we wanted to explore in the near future, including take advantage of the JEDI system to test or evaluate different ops operators, and also explore assimilation of the GNSSR, the ocean surface wind and the soil moisture data. And we're very interested in the PRO data and the utilization of this data in data simulation. That's all from me.
Thank you. We have time for one question.
Jonathan Brandmeier from Planet IQ. So I noticed that you have a 45-kilometer cutoff at high altitude for all commercial RO data.
Yes.
Today, it looks like both vendors are producing data comparable to Cosmic 2. Are you considering lifting that cutoff?
We're actually doing testing for that.
There's another urgent question. We can take it. Otherwise, let's thank the speaker again. Oh, Ben?
The new QC and the error, it seems like neutral. Why do you think that's the difference? That's curious.
You're asking why it is the impact is neutral, or? Yeah, I guess even though the new QC bring into a lot of data in the troposphere and also upper atmosphere, that amount of data, I guess the impact, I don't have a direct answer for that, but it seems from the result that the impact is not significant enough.
Actually, more data knows the time.
Have more data, what?
To increase the observation error. we can discuss this offline.